Hello, in this video we'll be doing question 15, which is some constraint optimization. Part 1 asks us to write a Lagrangian of the constraint optimization problem that we're given. So let's do that. The Lagrangian that we're writing out is, and the way that we write out Lagrangians is we take what's inside our minimization, and if you're given a maximization, so for instance if this said max, I would adjust this equation in order to make it a minimization problem that's equivalent, and then I would write it down. That is not the right pen. 2x squared, x1 squared plus x2. And then we take our such that clauses and we move them so that there's a 0 on one side. The precise way in which you do it doesn't actually matter because your lambda could, your constraint multiplier could be positive or negative, and it won't really affect it, if that makes sense. So in this case, you could also do, I could bring the 4 over here, and then all that would happen is that when you solve this, your lambda would be the negative of what it would be if you did it the way that I did it, but it doesn't really make a functional difference. Okay, and we now need to do our last such that clause, and here we see that there's already a 0 on one side, so there is no need to adjust that. So we have our multiplier, which will be gamma. It's a bad gamma. So this is our Lagrangian. So now, for the second part, write out our 4 KKT conditions. The first one is stationary condition. For a reminder, you don't have to write this, but you do have to write at least the stationary condition name. So this is that all derivatives of L equals 0. So the derivative is 0. So write this out. dl dx. And that is the wrong L that I wrote. And you notice that we have x1 and x2, so we derive the top with respect to x1 and the bottom with respect to x2. So here we would have 4x1 plus 3 lambda plus gamma. And here we would have 1 plus, wait, that's the wrong x there. It's a minus 1 lambda plus 3 lambda, and then this equals 0, 0. So then we have 2.2. Our second condition is primal feasibility. So this, you don't have to write this down, but for reference, this is all constraints are satisfied. Some terrible writing. So we have our two constraints, our two such that clauses. So x1 minus 3x2 equals 4. And we have x1 is less than or equal to 0. For 2.3, we have the dual feasibility. So all duals, all dual vars, so all dual variables are non-negative. So we have gamma I is greater than or equal to 0 for all I. I believe this is how we write this. And finally, for 2.4, we have I honestly forgot the name. Let me look. It's a complementary slackness, right? But what I do remember is that it's just y times x equals 0 in this case. Which means that gamma x1 equals 0, which means that gamma equals 0. I'll elaborate on that later. So we've written out our 4 KKT conditions, and what's left is to solve, which is what part 3 asks for, optimal solution x star and lambda star. So let's use our KKT conditions. The KKT conditions, as a reminder, are just basically a sort of check the list strategy that just lists all information that we're given in specific ways in order to make it very clear like what we're working with and be very clear about like what needs to be true in order for us to find the optimal solution. So the KKT basically gives us as many different equations as possible in order to basically create a system of equations where there's like no way that we'll have the situation where we have too many unknowns for the amount of equations that we have. So if we just look around here, if we reason through this, complementary slackness is really the principle that one of our such that's needs to be equal to 0, and because x1 is greater than or equal to 0, and we know that that is going to be a non-active because x1 is not going to be 0, we have that gamma here is going to be 0. And because gamma is 0, x1 can be anything, but that does satisfy complementary slackness, and by gamma being 0, well, we do have this gamma. So we can then plug in 0 there, and maybe we might get some interesting numbers. So let's use this. So we see, for instance, maybe I should, no better colors, but 1 plus 3 lambda equals 0. So already I can tell you lambda equals negative 1/3, because if 1 plus 3 lambda is 0, then lambda must equals 1, negative 1/3. Then we see that 4x1 minus lambda equals 0. So 4x1 minus lambda equals 0. Well, that means that 4x1 equals, I believe, negative 1/3. So x1 equals negative 1/12. Then, using that, we can plug that into here, and it's true. And we can also plug that into here to find x2. So let's do that. We have negative 1/12 minus 3x2 equals 4. So what we can do here is we can add. So negative 3x2 equals, and I believe this is 4 plus 1/12, so this is 49/48. And then we can, that is not 49/48, that is 49/12. And then we divide by negative 3, so x2 equals 49/36 negative. So we know x1, we know x2, and we know lambda. Let's just verify that all of these KKT clauses are true. That's true, because if gamma is 0, then it's always going to be equal to 0. So it's not negative. This is already true. We did that earlier. And all of these are true. So we did that. So all of our KKT conditions are true. And we have our answers to our problem, where x star equals negative 1 over 12, negative 49 over 36, and lambda star equals negative 1 over 3. All right, so that's how you do problem 15. Good luck on the rest of your studying.